All right. So today we're going to talk about chemical equilibrium. Okay. So objectives for this lesson, at the end of this lesson, you'll be able to describe equilibrium from an atomic or molecular perspective. What's going on at the atomic level in terms of equilibrium? You need to be able to calculate the reaction quotient and the equilibrium constant and make a distinction between the two. You need to be able to predict the direction of reaction by comparing reaction quotient and the equilibrium constant. Which way will the reaction go, forward or reverse? You should be able to calculate equilibrium constants from experimental data as well as literature values. Predict how far reactions will go based on the equilibrium constant and initial constant conditions. And we're going to talk about Le Chatelier's principle, and you can use that to predict how a system that's already at equilibrium will shift in response to stresses. And we'll also be able to explain Le Chatelier's principle in terms of the relationship between the reaction quotient and the equilibrium constant. That's a lot of objectives. So. All right, so concept of equilibrium. Typically, when you have a reaction, the profiles for the reactants and products would look like this. Which curve? This is concentration of reactant or product versus time. Which curve here would represent the reactant, and which one would represent a product? The red curve would represent reactant, and the blue curve would represent your product. Okay, so when is this reaction fastest? At the beginning, right, where the slope of your curve is steepest. And when is its lowest? Over time, concentrations level off, the rate of the reaction essentially goes to zero. We say when that happens, we say we've reached equilibrium. Okay, so equilibrium at the molecular level, what actually happens is the reaction has not really stopped. Forward reaction is still going, except that reactions are reversible. So what we're saying is at equilibrium, the forward reaction is occurring as fast as the reverse reaction. So overall, you don't see any net change in your reaction mixture. Okay, so no further changes are observed. So chemical equilibrium, we say, is a dynamic equilibrium. Okay, at the microscopic level, at the atomic level, nothing has really stopped. The reactions are still going on, except that the forward and reverse reactions are going at the same rate. Why is the reactant not completely used up in this particular example? You'll notice your reactant levels off at some value, not zero. Okay, typically that would be the case because sometimes depends on how. Because that would depend on how fast the forward and reverse reactions occur. Okay, so we say reaction is essentially complete if the reverse reaction is very slow compared, is the rate constant. Remember we talked about kinetics. The rate constant of the reverse reaction is very small compared to the rate constant of the forward reaction. If you remember, we said the rate for the forward reaction, let's say, if you have something as simple as R going to P, let's say you have an elementary step, right? So the rate of the forward reaction would be what? B forward would be K times concentration of R, right? K forward. We're going to label that with an F. And the rate of the reverse reaction would be equal to K of the reverse reaction times the concentration of the product. We say at equilibrium, these two are equal. Okay, this and this are equal at equilibrium. And then what would you say would happen? If those two are equal, then you say Kf times R must be equal to Kr times P at equilibrium. Okay, so you say Kf over Kr is equal to P, concentration of P over concentration of R. Okay, so what would be the conditions that would lead to a preponderance or predominance of product at equilibrium? If we want a lot of products at equilibrium, how would the Kf and the Kr be related? If you want this ratio right here to be really big, that means Kf If Kf is much, much larger than Kr, then you say your reaction is essentially complete, right? This ratio is going to be a very big number if Kf is much, much larger than Kr. So the extent to which your reaction goes all the way to the product side depends on your rate constants. But the rates at equilibrium for forward and reverse are equal. Okay? It's the rate constants that determine how fast the reaction, how far the reaction will go. So here's a quick question. Click a question that will check your understanding of the concept of equilibrium. Consider a reaction illustrated here. This is at time 0, 2 minutes, 4 minutes, 6 minutes, 8 minutes, 10 minutes. What's happening here? Your red atoms are being converted to what? It's changing to blue, right? So what's happening here? From time 0 to time 2 minutes, what happened? You lost how many red atoms? You've lost 4 red atoms, okay? And they're now converted into molecules. I colored the molecules blue just to emphasize that they've been turned into molecules, okay? So that's your reaction right there. So if you have the reaction here is you have 2 red atoms exchanging to a blue molecule, right? Or an R2 molecule, you can say. That's your reaction. So when did this reaction reach equilibrium? Between 2 and 4 minutes, at 4 minutes, between 4 and 6 minutes, or after 6 minutes? Alright, let's see. 50-50. What's the popular answers? A and B? Alright. Okay. Let's convince your neighbor your answer is right. Who picked A and who picked B? Okay. Why did you pick B? Okay, so there hasn't been any change since 4 minutes. Okay, what about you, Brandon? Okay. All right, so let's do the redo the poll. Let's see how we did this time. A is the better answer, right? You know at 4, it's at equilibrium, right? It hasn't changed since 4 until 10 minutes, but you don't know if that could have happened before the 4-minute mark. You know it's happened somewhere between the 2-minute mark and the 4-minute mark, okay? All right. What determines equilibrium? For a given reaction at a given temperature, the reaction quotient reaches a constant value. And that reaction quotient Q, we're going to define that in just a little bit. That reaction quotient, you calculate that from what we call activities of the species that are involved in the reaction. A species is our generic term for either an atom, an ion, or a molecule that's involved in a reaction. Okay? So for every reaction, there's a thing called a reaction quotient. It's a number that we can calculate, okay, which depends on the activities of the particles that are involved in that reaction, okay? Now, for a precise definition of what activity is, you're going to have to take an advanced course in chemical thermodynamics, and that's physical chemistry. And I teach that in the fall, actually in the spring, okay? So, but we're going to simplify things at this level. We're just going to say that these activities these are unitless quantities, by the way. we'll just approximate them. These activities are related to concentration and pressure, and so we're at this level. We're just going to say if we're dealing with a pure liquid or a solid, the activity is 1. Okay. If you're dealing with solutes in dilute solution, then the activity is just the molality. Now, since we are going to be doing mostly aqueous solutions, remember, if you have a very dilute aqueous solution, molality is essentially molarity. So for our purposes, we're just going to be using molarity as our activity. Okay, so pure solid or liquid activity is 1. Dilute aqueous solution, the activity is the molarity. It's just the numerical value, okay, no units. If you're dealing with a solvent in dilute solution, the activity is the mole fraction of the solvent in your mixture. And that's going to be essentially 1 for most practical purposes. Since we're going to be dealing with aqueous solutions, dilute aqueous solutions, we're just going to say we're going to just use 1 for our solvent. So the activity of water in a dilute solution, we'll just say it's essentially 1. And if we're dealing with a gas, then the activity will be just the numerical value of the partial pressure in atmospheres. Okay? Actually, the modern standard, the modern definition is you have to use bar, which is 1 atmosphere is 1.01325 bar. Okay? So that means you're about 1% off. But most general chemistry textbooks still use atmosphere, so we're going to stick with atmosphere. Okay? But if you do get to physical chemistry, our activities for what we call an ideal gas case would be the partial pressure, the numerical value of the partial pressure in water. Okay. So here's a quick question. If you have 0.01 molar barium chloride solution, what would be the activity of chloride ions? In other words, what would be the molar concentration of chloride ions? Okay. Remember the brackets mean concentration in moles per liter, right? So what's the numerical value of the concentration of chloride ions in a 0.010 molar barium chloride solution? Is it A, 0.010, and so on? Okay. Let's go ahead and do a poll. Correct answer. What did we say activity was? It's a unitless quantity. It's for solids. In aqueous solutions, it's the numerical value of the molar concentration. So which one can you rule out right away? No unit, right? So this one, oops, that one's wrong. Okay. What's the concentration of chloride? What happens to barium chloride in water? It breaks up into barium ions and 2 chloride ions, right? So if you have 0.01 moles of barium chloride, that's actually 0.02 moles of chloride. So 2 times 0.01 would be 0.02. Very good. Correct answer is C. Okay. So how do you calculate the reaction quotient? This is the procedure for calculating the reaction quotient. Well, it's a quotient, so it's a fraction, right? There's a numerator and a denominator. The numerator is calculated by multiplying the activities of the products of the reaction, what you wrote as the products when you wrote the chemical equation. But you have to raise each activity to a power equal to its coefficient in the chemical equation. You do the same thing for the denominator, except in the denominator you do it for the reactants. So, in other words, reaction quotient is some quantity based on the activities of the products divided by a quantity based on the activities of the reactants. Let's illustrate that with this example right here. What would be the reaction quotient for this reaction? What are our products? H2 and magnesium ion. So what is the activity of H2 gas? The numerical value of the pressure in the partial pressure of H2 in atmosphere. So it's partial pressure of hydrogen. Okay, it's unitless. Okay, Now, keep in mind when I say partial pressure of H2 here, I'm only referring to the numerical value. If you really want to be strict about units, you can say that's pH2 over P naught. And P naught, we say, like, in this case, would be 1 atmosphere. So if, like, you have 0.5 atmosphere over 1 atmosphere, then the ratio of the two is just 0.5. Okay, but things can get cumbersome if we do it that way. If for precise, if you want to use precise mathematical language, that's what you have to do. That's what we do in physical chemistry. Okay. So anyway, it's P over P partial pressure of H2. What would be the activity of magnesium ions? These are ions in solution. So what would be the activity of that? Molar concentration. So I'm going to write Mg with a +2. So that's my numerator. To what exponent should I raise my H2? What's the coefficient of H2 here? It's 1, so raise to the power 1. If you raise something to the power 1, you don't have to write the 1, right? And to what power should I raise my magnesium? Also to the power 1, so I don't have to worry about putting that. So divided by, what about a solid? What's the activity of a solid? Go back to the previous slide. Activity of a solid is 1. Pure solid or liquid, activity is 1. So 1. And what's activity of H plus? It's an aqueous solution. It's a solid, so concentration of H plus. But what should I do with that? Raise that to the power 2. Okay? So that's how you calculate your reaction quotient. You figure out what's the partial pressure of H2, what's the concentration of magnesium in moles per liter, what's the concentration of H plus in moles per liter. Plug it into this expression. Make sure you don't forget to raise the activities to exponents corresponding to the coefficient in the balance equation. All right, so let's look at this example right here. How would you calculate Q for this? Given that at a particular instant you find that H2S is 0.1, H3O plus is 0.15, and sulfide is 0.020. What would be our Q for this one? It's going to be H3O plus raised to what power? Products over reactants, right? Raised to the power 2. Concentration of, what's the other product? Sulfide, raised to what power? 1. So I don't have to write 1, right? Over H2S. It's an aqueous solution, so concentration of H2S raised to what power? 1. And do I do concentration of water? No, it's just, what's the activity of liquid water? It's actually the solvent here, mole fraction, but for practical purposes, that's just going to be a 1. And raised to what power? 1 squared is still 1, right? So you can just ignore that one. All right, so let's plug in our numbers. What are the numbers? H3O plus is how much? 0.15 squared. And sulfide is 0.020 divided by H2S, which is 0.10. Okay? So that should give you how much? I am recording this, huh? Yeah. Okay. It's going to be 0.15 times 0.15, that makes it a square, times 0.02 divided by 0.1, that's 0.0045. Okay. So our reaction quotient in this particular case is 0.0045. Or 4.5 times 10 to the negative 3. And it's a unitless quantity, okay? All right. Now, we said that for a given reaction at a given temperature, okay, the value of the reaction quotient approaches a constant value same value every time when it reaches equilibrium. So that value that it approaches is called the equilibrium constant. We call it K or KEQ. Okay? So that's a constant at a given temperature for a given reaction. So if you have Q, okay, Q can be at any given time, whether the reaction is at equilibrium or not, you can calculate Q. But once the reaction is at equilibrium, it will always have that same value for a particular reaction at a given temperature, and that value is going to be equal to KEQ. Okay? So let's look at an example here. How do we determine the KEQ? You can basically just carry out the reaction, okay, and determine the activities of the reactants and products at equilibrium. Let the reaction go all the way until it stops, until it reaches equilibrium. Then measure the activities of the reactants and products. So let's illustrate that with this simple example. Let's say you have X. 1 mole of X yields 3 moles of Y in aqueous solution. You let this reaction go to equilibrium. Okay, let's say you start off with a mixture that has 0.1 molar X and 0.1 molar Y to begin with. So the activity of X is 0.1, activity of Y is 0.1 at the beginning. Okay, you mix some X and Y, and then you let it run until it reaches equilibrium. Okay, how do you know it's reached equilibrium? When the concentrations of the reactants and products are no longer changing, right? So you find a way to monitor the concentration of X or monitor the concentration of Y. So let's say the reaction has reached equilibrium, and by the time it's reached equilibrium, the concentration of X is only 0.05. Okay, what's the KEQ for this reaction? What we can do is we can construct what's called an ice table. It's a very convenient way of doing this. So X, okay, aqueous, yields 3Y, aqueous. And you make a table. You start off with an initial concentration. What's our initial concentration of X? 0.1, right? And what's the initial concentration of Y? Also given in this problem to be 0.1. Okay. What would be the changes? If the reaction were to go forward, first of all, did this reaction go forward or reverse? I ended up with, let's look at the equilibrium values. My equilibrium value for X is 0.050. What happened to my X? It dropped from 0.1 to 0.05. By how much did it drop? Point what? 0.050, right? Okay. So if I lost 0.050 moles per liter of X, how much Y did I make? If I were to lose X moles of X, how many moles of Y would I make? 3:1, the balance equation. So I'm going to make 3X moles of Y per liter. Okay, if I lost X moles of X per liter, then I'm going to make 3X moles of Y per liter. So what's the change in Y going to be? It's going to be plus what? 3 times 0.05, right? Because we can identify that X is 0.05. So how much Y do I have now? It's going to be 0.100 plus 3 times 0.05. Okay? So we're assuming we have a liter of solution. So these are the moles in that 1 liter of mixture. So what's our reaction quotient? Initially, what's our reaction quotient? How do I calculate reaction quotient? Concentration of Y cubed over concentration of X, right? Remember, products over reactants. So what's the concentration of Y? 0.100 cubed divided by concentration of X is 0.100. So what is my Q at the beginning of this reaction? Initially, my Q is 0.01. Okay, 0.0100. What is my Q at equilibrium? 0.001. So it's 1.00. Okay, 1.00 times 10 to the negative 4. So what's my Q at equilibrium? This is 10 to the negative 2 cubed over 10 to the negative 2. That's 10 to the negative 4. Oh, it is 0.1. Oh. It's 10 to the negative 1 over 10. So it's 10. I had it right. Okay, so it's 10 to the negative 2. Okay. All right, so it's 10 to the negative 2. What's my Q at equilibrium? What do I have at equilibrium? This one right here. That's my Y at equilibrium, right? So that's going to be what's 0.1 plus 3 times 0.05? 0.25? Okay, so this is 0.25. Okay, 0.250 actually. So 0.250, so I have to cube that. And what's my denominator now? It's not 0.1 anymore, it's now 0.05. So divided by 0.05. So what's 0.25 cubed over 0.05? 0.25 raised to the power 3 divided by 0.05 equals 0.3125. So 0.3125. So that's 0.31, right? 312. This is going to be what? 0.0100. So what happened to my Q? From 0.01, it went up to 0.313. It went up or down? You can see that as this reaction goes forward, you're making more numerator, right? You're making more products. Your Q increases. Okay? And so what's the KQ for this reaction? Is it 0.01 or 0.313? You're asked for the equilibrium constant. Okay? What's the KEQ for this reaction? Is it A? Let's see if you've been paying attention. Is it 0.01 or is it 0.313? That's the KEQ. Okay. Correct answer is 0.313. That's the value of Q at equilibrium, right? And it's going to stay there forever unless you disturb your system. You do something to it. It's reached equilibrium. That's the value of Q. So for as long as you're looking at the same reaction, for that particular reaction at that temperature, that would be your equilibrium constant. Okay, so it's pretty straightforward. You just have to know how to calculate the reaction quotient. Whatever the value of the reaction quotient at equilibrium is, that's your equilibrium constant. Now, for gas phase reactions, activities are typically given in pressure, as we mentioned earlier. But sometimes you can have activities expressed in terms of concentration. So you need to be aware of this, okay? And what do we mean by concentration in the gas phase? If you recall your ideal gas law, PV equals nRT, we can rearrange this to say what? That P is equal to N over V times RT, right? So that means what's N over V? Moles per liter. So that's concentration. So I can write that as CRT. Okay? So if that's the case, then what is Kp? Let's look at a simple reaction. All right? Let's say you have A gas going to 2B gas. Okay? What is our Kp? It's equal to pressure of B squared divided by pressure of A, right? That's activities for a gas is pressure, correct? But what if I want to use concentration instead? What's pressure of B equal to? Concentration of B times RT, that's the pressure of B, right? So I can rewrite that and then square it. That's my numerator. What's my denominator going to be? Pressure of A would be concentration of A times RT. And this one I'm going to raise to the power 1. What is this 2 and 1? That's the coefficient of A and B in your balance equation, right? Okay, let's do a little math review. If we have x to the n over x to the m, what's the answer? How can you simplify that? That's x to the n minus m, right? So like if you have x cubed over x squared, what do you get? X to the 3 minus 1, minus 2, which is x to the 1, right? So I can simplify this. I can say this is concentration of B over concentration of A times RT raised to the power 2 minus 1. Okay? So this gives me equal to, what is this concentration of, oh, this should be concentration of B squared. Sorry about that. So this is concentration of B squared over concentration of A. I'm just collecting all my RTs. Okay? So this thing right here, concentration of B squared over concentration of A squared, that's just Kc. Okay? So Kc times RT raised to the power 2 minus 1 is what we would call the change in the moles of gas when you carry out the reaction. Okay, so Kp will just be equal to Kc times RT raised to the power delta N gas. Okay, so what I call concentration of A here, and that's essentially this one right here. So that's moles of A over V, that's piece of A over RT. Uh-huh. Okay. Let me do this step by step. Let's go from here. Okay. So this is gonna be CB squared times RT squared. Okay. And this denominator is gonna be CA times RT. Okay. If you have x times y squared, that's the same thing as x squared y squared. Okay. So that's why that 2 still stays with the c sub b. Okay, so now that's going to be k sub c. This thing is k sub c, and this thing right here would be RT raised to the power 2 minus 1. Okay, so a good way to remember this is to say that pressure is equal to CRT, right? Concentration times RT, where C is N over V. So Kp would just be Kc times RT raised to the power delta N gas. Because your numerators will be multiplied by RT to the whatever coefficients of the products are, and your denominator will be multiplied by RT raised to the power equal to the sum of the coefficients of your reactants, just for the gas phase. Okay, so let's illustrate that with this clicker question. How is Kp related to Kc for the following reaction? A gas gives you 2B gas. Okay. 50-50 again. Half of you fell for the trick, I guess. No, maybe not. All right. Delta N gas for this is 2 moles of gas on the product side. How many moles of gas on the left side? 1. So 2 minus 1 is 1. So we say Kp is equal to Kc times RT raised to the power 1. Do you have any equation that shows that? It's Kp on the left, Kc on the right.
There's no right answer.
Yes, there is. Because what if I divide both sides by RT? Divide both sides by RT. What do you get? Kc is equal to, it's going to be equal to Kp over RT, right? So that's another way of writing it. So that's Kp over RT to the delta N gas. So that's going to be equal to Kp times RT to the negative 1. So which one's the correct answer? No. Correct answer is C. I guess more, not just half fell for the trick. It's the whole class. How about, let's try this one. A goes to B gas. What if K? Suppose you found Kp to be 10. What would be Kc? What's the relationship again? Kp equals Kc times RT raised to the delta N. What's delta N gas here? 2 moles of gas in the product, 1 mole in the reactant. That's going to be 2 minus 1 is equal to 1 Kc RT to the 1. So if I want to solve for Kc, Kc would be Kp over RT, right? So what would it be? What's our Kp? 10.0. What's my R and what's my T? My T is 298 Kelvin. Unless otherwise specified, assume it's 298 Kelvin, okay? But it is given here as 298, so you're okay there. What's our case? What's our R? Since our pressure is given in atmospheres, your R would be 0.08206, okay, liter atmosphere per mole Kelvin, okay? But you really don't need to put the units there. Just keep in mind that since Kp is in terms of atmosphere, okay, because you really shouldn't be putting any units here, okay? So let's just do it that way. So what would be 10 divided by 0.08206 times 298? And divided by 0.08206 divided by 298. So it's going to be 0.409. Okay. Now, if you are doing Kp in terms of bars, okay, which is the modern way of doing it, then you divide by 0.08314. That would be liter bar instead of liter atmosphere per mole Kelvin. Okay, but like I said, we're just going to stick with atmosphere since your book does that. So you use 0.08206. Okay. All right. How is Kp and Kc related in the following reaction? Calcium carbonate solid gives you calcium oxide solid plus CO2 gas. Let's see if you do better on this one. Okay, let's see. Popular answer is C. Why is C? What's delta N gas here? How many moles of gas do you have on the product side? 1. This is a solid, right? So that doesn't count. So 1 mole of gas on the product side. How many moles of gas do you have on the reactant side? None, because that's a solid. That doesn't count. So delta N gas is equal to 1. So we say that Kp equals Kc times RT. So what is Kc? Kp times RT to the negative 1. So correct answer is C.
I'll put that, but I didn't do it right. I took the 3 from the CO2 and subtracted it from the 2. Like, you see what I'm saying? And then, wait, CaCO3,
Uh-huh.
took that 3 and then I subtracted from CO2.
No, not,
And I got 1, and you had to reverse it.
no, you have to look
So
at the coefficient.
you just look at the one in the front.
You just look at the coefficients of the substances that are in gaseous form.
Okay.
Yeah. All right, so you can determine KEQ from other reactions in a manner that's similar to what you did with delta H's for Hess's law, except in this case you don't add or subtract things. You take reciprocals and you multiply. Okay. So for example, if A going to B is equal to has a KEQ equal to X, right? So what's the expression for KEQ? That's concentration of B over concentration of A, right? Products over reactants. So what would be KEQ, and this would be the values at equilibrium, right? What would be KEQ for this second reaction right here? This is going to be A over B, right? The product in this case is A, and the reactant is B. So you can see if you flip a reaction, what happens to the KEQ? Do you take the negative of it, or do you take the reciprocal of it? Reciprocal. So KEQ for this is going to be 1 over X. Now you can combine two reactions. Let's say this reaction right here, A plus A going to B has a KEQ of X, and then C going to D has a KEQ of Y. What happens if you combine those two? Well, let's see. KEQ for the first one, for this one, KEQ is B over A, right? What's the KEQ for this second one? It's going to be B over C, right? Products over reactants. What's the KEQ for this overall reaction? Products, B times D over reactants, so concentration of A, concentration of C. What do you notice here? B over A is X, right? And D over C is Y. So KEQ here is equal to X times Y. So if you add up two reactions, you'll find that the KEQ for the resulting reaction is just the product of the original KEQs. Okay? So here's a clicker question for you. A to B has a KEQ of 2.0. That's the KEQ for 2B going to 2A. What did I do? I flipped it and I doubled it, right? Okay. Correct. The answer is 0.25. Very good. When you flip it, B goes to A. The KEQ for this is going to be 1 over 2, right? Now, if I double it, it's just like I'm adding another one. That gives me 2B goes to 2A. So KEQ here would be 1/2 times 1/2, which is going to be 0.25. Okay? So you flip a reaction, KEQ is a reciprocal. You add two reactions, you multiply. So if you add two identical reactions, that means you double the coefficients in your balance equation. You just square the KEQ. Okay? So that's what's again. Let's talk about the net direction that a reaction will follow when it occurs. All you have to do is compare Q versus KEQ. What happens if Q is less than KEQ? Well, if KEQ is over here, let me do it this way. let's draw a number line. If KEQ is over here and Q is over here, okay, what will happen? The reaction will have to occur so that eventually Q becomes equal to KEQ, right? So Q will have to increase until it becomes equal to KEQ. Because if Q decreases, it cannot be equal to KEQ if it's less than KEQ, right? How can Q increase? How do you calculate Q? Something that depends on the products over something that depends on the reactants, right? How can you increase Q? You make more products, right? So you need to shift to the right. So we say there will be a net forward reaction until Q becomes equal to KEQ. So this is an easy way to remember it. If Q is less than KEQ, the reaction is going to shift forward, going to go forward until Q becomes equal to KEQ. Okay? So the forward reaction makes Q larger because that's going to give you more products. So your numerator is going to increase. What happens if Q is larger than KEQ? If Q is over here? Then we say there will be a net reverse reaction. Okay, the reverse reaction will predominate until Q becomes equal to KQ, and you have reached your equilibrium. Okay, so let's do a few clicker questions. We have A going to B. 1 mole of A gives you 2 moles of B in aqueous solution. KQ is 10. Which way will the net reaction occur in a mixture where if Q happens to be 0.1? Is it going to go forward, reverse, or neither? If Q is less than KEQ, it goes forward. Okay? And here's your KEQ. If Q is less than KEQ, it goes forward. Okay? Here. Slightly more complicated. Same reaction, same KEQ. Which way will the net reaction occur if for this particular reaction mixture you have a concentration of 0.1 for A and there is no B? Will the reaction go forward, reverse, or neither? All right. Well, what's our Q? How do you calculate Q? Products over reactants. What's our product? B, right? What do you do to B? Square it, and a reactant? A. So what's the concentration of B right now? 0. 0 squared over 0.100 is... So how does Q compare to KEQ? KEQ is 10. Where is Q? Where is 0? Q is 0. So which way will it go? Forward. Okay. Next question. This time, think of it this way. You don't have any B. The only way for the reaction to go is forward, right? You can't go reverse. There's no way. There's no B that you can use out. Okay. Let's look at this one. Which way will the net reaction occur in a mixture where A is 0 and B is 0.1? Is it going to go forward, reverse, or neither? What's a number divided by 0? Infinite. So, Q would be equal to B over A, right? So it's b squared over a. So it's 0.100 over 0. Divide by a smaller number, you make q very big, right? In fact, this approaches infinity. So the only way for the reaction to go is to the left. Q is very large, okay, over here at infinity, and KEQ is down here at 10. Okay, so correct answer is reverse. Let's try this one. A is 0.1, B is 0.1, same reaction, same KEQ. Will it go forward or reverse? Or is it at equilibrium already? Okay. Most say forward. Let's see. Q equals concentration of products over reactants. What's our product? B, and then you square it over A. And so what's our Q in this case? 0.1 squared divided by A, which is 0.1. What is 0.1 squared over 0.1? 0.1. Is that less than, greater than, or equal to KEQ? Less than 10.0, which is our KEQ. So reaction will go forward. Finally. All right. So now that we know if a reaction is going to go forward or reverse, we can actually figure out if we know the reaction, we know the equilibrium constant, and we know the initial concentration, then we can figure out what will we have at equilibrium. Okay? So if you know the initial concentrations, or actually the activities, and you know what the KEQ is for your reaction, you can predict how far the reaction will go. What are you going to have at equilibrium? When the reaction stops, what will you have? Okay? And so the procedure for this, similar to what we did earlier, you set up an ICE table. What does ICE stand for? Initial concentration or initial activities, changes, and then the equilibrium values. Okay? And then what you do with the initial values is you compare your initial Q with your KEQ. So compare the initial value of Q with KEQ to determine which way the reaction will go. And then you let X be the extent of reaction, okay, in the direction that you've decided. And then you solve for X, knowing that Q must be equal to KEQ at equilibrium. Let's illustrate that with this problem right here. Let's say you have a reaction between A gas and B gas gives you 2AB gas. Okay? Oops. It's not balanced, huh? Let's just call this C gas. And let's say Kp happens to be 25. All right? What would be our initial activities, initial pressures? Partial pressure of A is 0.1. So initially A is 0.1. What's the initial value for partial pressure of B? It's also 0.1. And initial partial pressure of C, let's call this partial pressure of C, is also 0.1. Okay? And our Kp is 25. So what is our Q initially? It's going to be 0.1 squared over 0.1 times 0.1. Okay? So this is your C, pressure of C squared over pressure of A times pressure of B. So what is our value of Q initially? 1. Okay? 1.0, 2 sig figs. Okay? So that's our initial Q. Which way will the reaction go? Forward or reverse? Q is less than KP. KP is KQ, right? Q is less than KQ, so it will go forward. So what would be our changes? We don't know, so if we don't know something, you represent it by a letter, right? So I'm going to say I'm going to lose X atmospheres for that. I'm going to lose X atmospheres for B, and I'm going to gain how many atmospheres of C? 2X. Those would be my changes. Okay? Now, this is true if, assuming you are, and we're going to make this assumption that your volume of your container is fixed. Okay? All right, so what would be our change, our equilibrium values then? Partial pressure of A at equilibrium is going to be 0.10 minus X. What's the partial pressure of B at equilibrium? 0.10 minus X. And partial pressure of C at equilibrium is 0.10 plus 2X. So how do I solve for X? Well, I should know what Q at equilibrium is, right? So Q at equilibrium is Kp, and it's equal to how much? It's given as 25, right? And that's equal to what? Pressure of C squared over pressure of A times pressure of B. What's pressure of C squared? What's pressure of C? 0.10 plus 2x squared divided by pressure of A is 0.10 minus x, and pressure of B is 0.10 minus x. Okay? So here's the equation we need to solve. Let's rewrite this. And here you say 25.00 equals 0.10 plus 2x squared divided by 0.10 minus x. And that's just going to be squared, right? These two are the same. So I can just combine those two to make it squared. How do I solve for x here? Should you expand that? Expand your binomial in the numerator, expand your binomial in the denominator, collect terms, use the quadratic equation, solve for x. Yeah. But that would be the long way. There's actually a shortcut for this. What do you notice? It's squared on both sides, right? The numerator and the denominator are both squared, so you can actually simplify this problem. You can just say, take the square root of both sides. So what's the square root of 25? 5.00. And that doesn't even have to be a perfect square. You just need to take the square root of it, right? And keep in mind that this is plus or minus 5. Okay? That's plus or minus 5. And what's 0.1 plus 2x? You take the square root of the other side would be 0.10 plus 2x over 0.10 minus x. So now you can solve for x. Okay? And what kind of x would you want? The x you would want is the x that is, what's a reasonable value for x? It has to be a number less than 0.1, but it has to be positive. So if you solve for x and you find out that x is negative, then that's not an acceptable value for x. Okay? If you solve for x and you find that x is greater than 0.1, that means you're going to end up with a negative concentration of A. That's not going to be an acceptable value for x. So let's go ahead and do that. Let's try 5. Okay? 5 equals 0.10 plus 2x over 0.10 minus x. How would I solve this? 5 times 0.1 minus x equals 0.1 plus 2x. So that's 0.5 minus 5x equals 0.1 plus 2x. Adds 5x to both sides. I have 0.5 equals 0.1 plus 7x, right? Subtract 0.1 from both sides. 0.4 equals 7x. And so x equals 0.4 over 7. What's 0.4 divided by 7? going to be 0.057. Is that a reasonable value for x? It's less than 0.1 and it's positive, so you're good. Okay? What if you did the other one? What if you did -5 equals 0.10 plus 2x over 0.10 minus x? What would you get? It's going to be -5 times 0.1 minus x equals 0.10 plus 2x. So that's going to be negative 0.5 plus 5x, right, equals 0.10 plus 2x. You subtract 2x from both sides, so this is negative 0.5 plus 3x equals 0.10. Add 0.5 to both sides, you have 3x equals 0.15. And x equals 0.15 divided by 3 is 0.05. Two possible answers. Am I missing something here? 0.05 is also reasonable, huh? Oh, it's plus 0.5. Okay. All right. That always gets me, the arithmetic. 0.1 plus 0.5 is 0.6. Okay. All right. So 0.6 divided by 3 is 0.2, right? And 0.2 is way larger than 0.1. If you lost 0.2, you'd end up with a negative pressure for A and B. So that's not acceptable. So always be alert to that when you're solving quadratic equations. Anything you've got, if you take the square root, okay, you have to worry about whether your answer is going to be reasonable. Make sure whenever you take your square root, positive, that you take into account the positive root and the negative root. So this one is not acceptable. So the answer is 0.057. So if you know it's 0.057, how do we finalize our answer here? Then you can say, okay, what did we say x was? X is 0.057. So we say at equilibrium, partial pressure of A is 0.10 minus 0.057 atmosphere. Partial pressure of B is 0.10 minus 0.057. And partial pressure of C is going to be 0.10 plus 2 times 0.057. And you can verify, you can always check if your answer is correct by plugging these numbers back into your expression for Q. And if you did that, you should find that Q will be equal to KEQ. Okay? You may be off a little bit on the last sig fig because of rounding errors. Okay, so that's how you do. Now, there's a simplifying assumption you can make if KEQ is very large, and usually anything larger than 10 to the third, you'd be able to make this assumption, or if it's very small, less than 10 to the negative 3. What does it mean when KEQ is very large? At equilibrium, what's favored? It's going to be mostly products, right? So you can assume the reaction is essentially complete. Shift it all the way to the product side. What happens if KEQ is very small? Then reactants are favored at equilibrium, right? So remember, a large KEQ favors the product, a very small KEQ favors reactants, okay? So you can assume you have complete reaction towards the preferred side, the product side or the reactant side, depending on whether your KEQ is very large or very small. And then what you do is you reverse the reaction by a very small amount, x, and then you can make approximations given that x is very small. So you can make some simplifying assumptions to make your calculation easier, you don't have to go through the quadratic equation and more complicated equations. Okay, so solve for x knowing that q equals keq at equilibrium. But if you do make these assumptions, make sure at the very end you verify if your assumption is correct. So let's see if we can illustrate that with this problem. What's the equilibrium pressure in a gas mixture? If you start with 0.1 atmosphere of A, 0.1 atmosphere of B, and 0.1 atmosphere, this is C, okay, not AB, C. And Kp happens to be 2.0 times 10 to the 10. Look at this number. Is that a very large or a very small number? So what do we expect at equilibrium? It's going to be mostly what? Mostly products. So, okay, so let's set up our ice table. A plus 2B gives you 3C. Initially, you're going to have 0.1 of A, 0.1 of B, and 0.1 of C, right? So, since we know at equilibrium, it's going to be mostly products, what do you expect? What would be the changes? You're going to lose all of your A, right? Or are you? If you lose X moles of A, let's just do it. Okay. If you lose X moles of A, how many moles of B am I going to lose? 2X, right? How many moles of C am I going to make? 3X, right? Now, what should my X be so that I end up with, my limiting reactant would be used up? It goes all the way. What if X is 0.1? Try X equals 0.1. So what's 0.1 minus 0.1? 0, right? What's 0.1 minus 2 times 0.1? What is 0.1 minus 2 times 0.1? Negative 0.1. Can I have negative pressure? No. So that means I cannot use up my A. I have a limiting reactant here. What's my limiting reactant? B. B will run out first, and so I'll have some excess A. So this is not going to work. X cannot be 0.1. Okay, so let's try a different X. This time we're going to say we're going to lose all of our B instead. Okay, so we're going to say 2X is equal to 0.1. Okay, not 2X. So what is 0.1 minus 2 times minus 2X? It's going to be 0, right? And so what's my X going to be? What's half of 0.1? Half of 10 is 5, right? So 0.05. So how much A would I have at equilibrium? This is going to be 0.10 minus X at equilibrium, or 0.05, right? And this is going to be 0, and this is going to be 0.10 plus 3x. What's 0.10 plus 3x? What is 3x? 3 times 0.05. That's 0.15 plus 0.1. That's 0.25, right? So this is 0.25. Well, it's not really going to go all the way, right? There's going to be a trace amount left here, so we're going to call this y. So we're going to lose a little bit y there, okay, and I'm going to get a little trace amount of y here. So this is going to be 0.050 plus y. So what would be my Q at equilibrium then? At equilibrium, we would say Q is equal to 0.25 minus y cubed over, that's your product, right? C cubed over A, which is 0.5 plus y raised to the power 1 times partial pressure of B is y squared. And And that's equal to KEQ, which at equilibrium is equal to 2.0 times 10 to the 10. Can I solve for y here? Should you be expanding your numerator?
The bottom should be 0.05.
0.050? Okay, I'm sorry. 0.050 plus y. What simplifying assumption can I make? I know that this y is just a trace amount, right? Because my favored side, I have a very large KEQ favoring the product. So I can say compared to 0.25, that y is going to be negligible. So I can neglect that. Compared to 0.05, that y is going to be negligible. I can neglect that. That makes it easy for the algebra now. What happens to your algebra now? It's 0.25 cubed over 0.05 times y squared equals 2.0 times 10 to the 10. How do I solve for y? So y squared equals 0.25 cubed over 0.05 times 2.0 times 10 to the 10. What would that be? Point 25 raised to the power 3 divided by 0.05 divided by 2 times 10 to the 10. That gives me, how many digits do I have there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Is that 11? Okay, so 1.5. Where is that? Oops, that's the wrong one. What? 1.56 times 10 to the negative 11. Okay? So what's my y? I take a square root of that. Oh, I lost it. Okay. 1.5 times 6 times 10 to the negative 11. Take the square root. So raised to the power of 0.5 equals 3.9 times 10 to the negative 6. 3.95. 3.95 times 10 to the negative 6. Okay, or you can say 4.0 times 10 to the negative 6. So that's a very small number, right? Now, is that a valid assumption? Did we make a good assumption? If I were to subtract 4 times 10 to the negative 6 from 25, would that still be 0.25? So 0.25 minus 4 times 10 to the negative 6. That's still 0.25. If I add 4 times 10 to the negative 6 to 0.05, will that still be 0.05? Yeah. So that's a valid assumption. Now, if you got a number that doesn't match your assumption, doesn't agree with your assumption, then you're in trouble. You're going to have to go back and actually solve for it correctly. Okay? And there's some numerical ways you can do it. You can, like, if you use Excel, for example, there's a technique there that you can use. It's a tool there called Solve For. You can solve for a value so that you can reach a particular goal, a goal seeker. Okay, so that's what you need to do. Right? This might be a good time to stop. Let's see. Let's do one more. Okay. Let's see what else. Oh, yeah. This would be one. Let's do one more. What would be the equilibrium concentration of H plus and hydroxide if you start with a mixture where H plus is 0.1 and OH is 0.2? Okay? So initially you have 0.1 for H plus and 0.200 moles per liter for hydroxide. And the KEQ for this reaction is 1 times 10 to the negative 14. Okay? What's our Q? Products over reactants. So it's going to be H plus over times hydroxide over activity of a liquid, 1. Right? So, and the exponents would be, coefficient here is 1, coefficient is 1, so that's 1 and 1 there. So H plus is 0.1, hydroxide is 0.20. What's our Q? 0.1 times 0.2 is 0.0200. Is that less than or greater than KEQ? Compare that to 1 times 10 to the negative 14. That's greater than KEQ. So which way will the reaction go? Left or right? Left, right? KEQ. Q is greater than KEQ. Reaction goes to the left. So the changes would be minus X plus X, right? And we really don't care about the water anymore because that's just going to be a 1 in terms of activities, right? So what would be the values at equilibrium then? This is going to be 0.100 minus X for H plus and 0.200 minus X for hydroxide. Now, can I make a simplification here? What is this KEQ? Is this considered a very big number, a very small number, or somewhere in between? A very small number. So it favors what? At equilibrium, it strongly favors reactants, right? So one of these two is going to get used up, right? Which one do you think is going to get used up? The 0.1. So this is going to be, and this is going to end up being essentially 0, right? Trace amounts. And what happens to 0.2? You lose 0.1 out of that, right? So your X is going to be equal to 0.1. So this is going to be 0.100. So what would I do to get my concentration, my actual concentration of H plus? Okay, so you need, now at this point Q is 0, right? Numerator is 0 because of this, if you put 0. So it's actually going to shift a little bit back to the right. So we're going to shift this back a little bit to the right. So I'm going to add plus y and plus y over here. So our KEQ then, 1.00 times 10 to the negative 14 equals y times 0.100 plus y. All right. What simplifying assumption can I make? I know that this y is a trace amount, so that's negligible compared to 0.1. How do I solve for y now? I can just say y equals 1.00 times 10 to the negative 14 over 0.100, and where y is going to be equal to, what would this be? 1.00 times 10 to the negative 13. Okay, and so y is my H plus concentration. And what's my hydroxide concentration? Is 0.100 plus y. So that is just going to be 0.100. Okay, let's verify that H plus times hydroxide is equal to KEQ. This is 10 to the negative 13 times 0.100. Okay, and you can see that in fact it is 1.00 times 10 to the negative 14. So our assumptions are correct. Okay? So that's how you solve. Solve problems where the KEQ is very large or very small. Anytime you see KEQs that are very large and very small, you should be thankful because that makes your problem easy. Okay? So this would be a good place to stop.